This is the second part of the module 8 regarding cost calculations at building level. In this second part, we will first of all focus on making an abstract model of our building by defining an equivalent box building. The second part of this session is the explanation of the calculation tool for the cost estimation of your projects. Let us start with the abstract model. In the first part of the cost calculation, we have seen the concept of introduced the concept of the ratios. So the ratios is a way, an approach to enable to link the geometric choices, design choices, to the material use of your building, and hence to the costs related to this. We have explained the ratios of the building by comparing these three buildings, two detached and one terrace building. And for the three buildings, we have calculated the ratio of the external walls. The ratio, as a wrap-up, the ratio is calculated by first of all calculating the floor area of the building. So for the first building, this means we have a square plan of 10 by 10 meters, meaning that we have a ground floor and a full floor of 100 square meters, as there is only one floor. Secondly, we calculate the external wall area. We have 4 facades. Each facade is 10 by 3 meters, so 30 square meters. 4 times is 120 square meters. This means that the ratio of the external wall is 120 square meter divided by 100 square meter, or we have 1.2 square meter of wall per square meter of floor area. The same calculation is done for the second example, where the floor area is again 100 square meter, but now the external wall area is larger. We have a front facade of 60 square meters, 20 by 3, the same for the back facade, so we have 60 square meters, and we have two side facades of 5 by 3, 15 square meter multiplied by 2, so we have 30 square meter side facades, in total 150 square meter. So the ratio of the external wall in the second case is 150 divided by 100 is 1.5 square meter of external wall per square meter of floor area. And the same exercise is done for the third example, where the external wall is more limited as we only have a front and back facade and no side facades. This led to a ratio of the external wall of 0.67, and for the three examples, the last one has the lowest square meters of external wall per square meter of floor area. These numbers can be compared, but it's easier if we compare these in a graphical way. So in the next slide, we again look at the ratios of the external wall, but also the other elements. So we have the same example. We have the three buildings analyzed before, and in the middle, in the dark brown, we see the graphical representation of the ratio of the external wall. How is it represented? Well, here we have a cube of 1 cubic meter, so each surface is 1 square meter. What we indicate on the cube here in the middle is the ratio of the external wall. The surface here, which is fully colored, is 1 square meter, so represents the number 1. And then we have 1/5 additionally of the next facade, which is 20%. So the 1.2 is represented as in this way for the first building. The second building had an external wall ratio of 1.5, which we can represent by a full area of 1 square meter and then another half, 1.5. The last third example had an external wall ratio of 0.93, so it's 9.3 centimeters, or 93% of the surface is colored. We can do the same for the other elements. So on the left in yellow we have the ratio of the floor, the ground floor. In gray, we have the ratio of the roof, and in orange, we have the ratio of the intermediate floors. So if we look at the calculation for the first one, the ground floor is 10 by 10 meters. If we divide it by the floor area, it's again 10 by 10 meters. We have a ratio of 1, so a fully colored surface on the floor. The roof is exactly the same. It's 10 by 10 divided by 10 by 10, it's 1. The same for this building. For the third building, we have another result, as now we have 3 floors. So the total floor area of the building is 150 square meters, namely 5 meter by 10 is 50 square meters multiplied by 3 floors, so 150 square meter floor area in total. If we calculate the ratio of the ground floor, it's the surface of the ground floor, 5 by 10, 50 square meter, divided by the full floor area, 150 square meter. So we have 50 divided by 150 is 1/3 or 0.33. The same for the roof. It's the same surface as the ground floor area, so we have the same ratio for the ground floor and the roof. For the intermediate floors, we have 2 intermediate floors. Each is 50 square meters, or so 100 square meter intermediate floor in total, divided by the total floor area 150, so it's 2/3 of 0.66, colored here in orange. And the same can be done for the internal surfaces, which I will not explain in detail, as you can't see the internal walls on the graph. But here we see an internal wall ratio of 0.90, 0.75, and of 2 graphically represented. Now, why do we graphically represent it? Because that allows you to easily compare the consequence of a certain design layout on these different ratios and amount of elements. So here what we see are 5 different buildings, each of them consisting on the same number of units, 64 units in total, but it's a different composition, so a different mass plan. For each of these 5 buildings, the ratios are calculated for each of these elements, for the foundation, for the external wall, for the internal wall, intermediate floors, and the roofs. This actually is the floor on grade, which is could be also a foundation, a floor foundation slab. What we see, for example, if we look again at the external walls, here we have an external wall of 0.5 square meter per square meter of floor area. The amount of external wall per square meter floor is lower for the second example, where it's only 0.38 square meters per square meter floor. It's higher for the third, as we have 0.56 square meters of facade per square meter floor, even higher for the next one, and highest for the last example. And that we can do for each of the different elements, and by then comparing them, we can easily see which elements have the highest ratios, and so the most expensive elements, we should try to reduce their amounts or their ratios in order to lower the investment cost. Now, most of the time, the floor plans of a building are not that simple as I have shown in the previous example. So very often they are more complex. Now, we will translate these complex floor plans to equivalent box buildings in order to make an easy comparison of your different projects. And again, we will graphically represent it to easily compare and interpret the differences. How will we do this? Well, we will translate your specific case to a box building. The box building has a rectangular floor plan, but keeps the same number of floors as your real building. So it's just changing a complex floor plan to a simplified floor plan. But the height, so the number of floors, remains identical as the real building. We will define the rectangular floor plan, so the width, for example, and the depth or the length and the width of the floor. We will define it in such a way that we obtain the same ratios for your real building and for the simplified box buildings for the roof, the floor, the external walls, and the internal walls. So, to clarify the concept, we again have our three examples, which are quite simple now to make a box building because these are box buildings. So for the first one, we have 3 times a grid of 3 by 3 meters. Our box building here is a box building, so if we represent it here on the grid, we have 3, 6, 9, 10 meters with 3, 6, 9, 10 meters. So it's exactly the same shape as we had in reality because we don't need to simplify. The second building is the same. We have 20 meters by 5 meters. So 20, 3, 6, 9, 12, 15, 18, and 2 meters is 20, and 3 plus 2 is 5 meters. So we have exactly the same form as we have in reality. And then for the last one, we have a floor plan of 5 by 10 meters. So we represent it here, 5 by 10 meters, 3, 6, 9, and 1 is 10. 3 plus 2 is 5 meters, so we have exactly the same floor plan as we have in our building. However, your building will typically have a more complex floor plan. So instead of having exactly the same width and length as in the real building, you will see that it will change. So I just took one example of all of your cases. It's the case analyzed by Rura El-Khalili, and what we see here is that this is one typical floor of the building, is that it's not a rectangular floor plan. We see that there are a lot of corners and different shapes of the outer walls of the building. So the aim is now to transform this building in a box building with a rectangular floor plan for each floor and the same floor plan for all floors. Now, how do we do this? How can we now transform this complex building or complex floor plan to a rectangular floor plan with a certain length and a certain depth of the building? Well, we do it as follows. It is in an Excel file, but you will first do it manually, so I'll explain how the calculations are being done, and then afterwards I can check if your calculations are correct, yes or no. So to ensure that I can check your calculations, you need to fill in your name and your country and a brief description of the project so I can identify who you are. Then you fill in the total floor area of all floors together. So if you have 6 floors, you add